All right, so the lesson today all has to do with shapes that we know are similar. So we're starting knowing they're similar. So we're going to say that our big idea here is that two similar figures. Now, what do we mean by similar figures? What does that mean about them? They're what? They're proportional. The sides are proportional. They're the same. We also said they're same size. They're the same shape, but not the same size. And in the last unit, we saw what kind of transformation gives us similar figures. Dilation. Dilation gives us similar figures. So we have two similar figures. Somehow we get similar figures. Two similar figures with corresponding sides in the ratio A over B. And for similar figures, what was the word that we used for the ratio that we made? We also used it in dilation. The ratio we made between the sides of the two figures. So if this was 2 to 3, for example, what do we call that when we had similar figures? Or when we did the dilation? Remember? We called that the scale factor. So the ratio of its sides of two similar figures is the scale factor between the similar figures. So that's the scale factor. Have areas in the ratio A squared over B squared. So what we're saying here is you square the side ratio to get the area ratio. We make a ratio of the sides of these two similar figures. We square that ratio. That tells us the ratio between the areas. And kind of a way to think of it is we know that our units for area are square units. So if our ratio is 1 inch over 1 inch, our area is inches over inches, our area ratio is going to be square inches over square inches. We have to square that to get our area ratio. The other thing that's important to know is that any length ratio between the two is the same as the side ratio. And what I mean by any length ratio is if we know the side ratio is A over B, the perimeter is the length. That ratio between the two similar figures is also going to be A over B because perimeter is a length. The ratio of the diagonal, the length of the diagonals, that's a length. That's also going to be A over B. The radius, the ratio of the radii of the two circles, it's going to be A over B. It's a length ratio. Any length ratio between the two similar figures is going to be A over B. Doesn't matter what that length is. And then our area ratio is going to be A squared over B squared. So that's our one idea for today. Side ratio is A over B, area ratio is A squared over B squared. So, questions so far? Yes. Let's do an example, and we'll hopefully you'll see it after an example. Okay. All right. So we'll start with similar rectangles. So we know these two rectangles are similar. Here are my two nice rectangles. There's rectangle 1, a rectangle 2. And we're going to say this is 8 millimeters and this is 6 millimeters. We want the ratio of the areas. And ratio of the perimeters. Well, all we know about these two is that they're similar, and we know the length of two sides. And I'm going to say we're going to do this for this problem. We'll do small to large. So our key, first thing we need to do is find the side ratio. So what's the side ratio of small to large of these two things? 6/8. We just make a ratio of the two sides. And can we reduce that to 3/4? Well, what we just talked about was that if we know the side ratio, to get the area ratio, we just square this. 3 squared over 4 squared. We get 9/16. So that's what we were just talking about. So if the ratio of the lengths between the sides is 3/4, the ratio of the areas is 9/16. So if the area of this is 9, the area of this one would be 16. And they would always be in that ratio. The perimeter ratio. Is perimeter a length? We measured perimeter with a ruler. Yeah? That's how we measure perimeter, right? Perimeter is a length. Well, any length ratio between these two is going to be the same. So it has to be the same as the side ratio. So it equals 3/4 also. Well, since they're similar, they're going to have the same ratio since they're proportional. So all we need for this problem, all we need to know is the length of one side of each of them. So that's the basic idea of what we talked about in the last one. Does that help it make sense a little bit, Amber? We're putting some numbers there. Right. Once you start doing it with some numbers, like, oh, okay, now I know what that is. Well, this isn't all we want to do with this. We want to solve problems with this idea. So in math, we like to create problems and then solve them. Okay, so let's look at how we would use this to solve some kind of problem. So we have these similar hexagons. And this is 7 feet, and this is 10 feet. And we know that the area of the smaller is 127.3 square feet. We want to find the area of the larger. So when we think about these problems, we should think about what we did in chapter 7 when we talked about similar figures. In chapter 7 we said, when in doubt, when we're solving problems with similar figures, what do? Cross multiply. So we're going to write a proportion. So to solve these kinds of problems, we should think, because we're dealing with similar figures, we want to write a proportion. That's our go-to method for solving problems with similar figures. Well, let's fill in the rest of this information we have. I'm going to do that in red. The area of this one is 127.3. The area of this one, we don't know, so let's call it x. We want to find x. We know they're similar. We know two sides. So let's start like we did on the last problem and write our side ratio. And I'm going to do the side ratio big to small here because we're trying to find x, and x is the big number. So let's put the big one on top. The side ratio is 10/7. Well, if we know the side ratio, how do we find the area ratio? Square it. So we have 10 squared over 7 squared equals 100 over 49. What is another way? Yeah. I chose the 10 because we're trying to find x. We're trying to find this area, and it's with the bigger one, so I thought let's put that on top. It doesn't really matter. It'll work either way. What's another way that we can write the area ratio? What's the area of the big figure? X. What's the area of the small figure? 127.3. Well, there's another area ratio. There are the area ratios of the same things. So what has to be true about this and this? They have to be the same. They have to equal each other. There's our proportion. 100 over 49 equals x over 127.3. So what we did was use the side ratio to come up with an area ratio. And then we used the information they gave us in the problem to write the area ratio in another way. But they're the area ratios of the same things, so they have to be equal. And then to solve this thing, I could cross multiply, and since I have the x on top here, I can just multiply both sides by 127.3. So those cancel. And I get x equals 127.3 times 100 divided by 49. I can plug that into my calculator, and I get 259.8 square feet. And there's my answer. So that's a kind of problem finding the area ratios lets us solve. We just wrote it in two different ways, one using the side ratio and one using the information in the problem. They have to be the same, so we set them equal to each other. Questions there? Okay. Let's look at one going the other direction. We can go the other direction as well. Let's say we know the area ratio. So I'm going to say the areas of two similar figures are 32 square meters and 50 square meters. And the problem asks us, what is the scale factor? Well, with the information we have, what's really the only thing that we can do? We know that they're similar. We have their areas. So what kind of ratio can we make? So Carolyn says we're going to square root the areas to get the side ratios. So I'm going to say the area ratio and we can do it either way. I'm going to do small to big. Doesn't matter. 32 to 50. And we know this equals a squared over b squared, where a over b is the side ratio. Well, I want a over b, not a squared over b squared. So to undo that square, we take the square root. So I take the square root. So the side ratio is the square root of 32 over the square root of 50. And here's a nice little thing that happens here. We work in simple radical form. Square root of 32 is 16 times 2. Square root of 50 is the square root of 25 times 2. Square root of 16 is 4 square root 2. Square root of 25 is 5 square root 2. And the square root of 2 divided by the square root of 2 cancels, and we get 4/5. Is the side ratio the same as the scale factor? That's how we find the scale factor, right? Figure out, make the ratio of the sides. Side ratio is 4/5. So the scale factor same as the side ratio, 4/5. So to go from the area ratio to the side ratio, we take the square root. That's what we want to talk about, the big picture idea here. So from area ratio to side ratio, take the square root. So we can go either way. We can go from the side ratio to the area ratio to the side ratio. From side to area we square, area to side we square root. What if this problem asks us to find the ratio of the lengths of the diagonals? What would that be? The side ratio. It said the ratio of the perimeters. Side ratio. The ratio of the, I don't know, what did I say? Two similar figures. If they were hexagons, the ratio of the apophthegms would be 4/5. So any length ratio is going to be 4/5. All right, questions? Okay, that's all we're talking about today. There we go.